Isotopes. All right, ISA, huh? Okay, so let's talk about isotopes. It's a very simple process. All right, so let's assume, let's keep what we did before here. I'm going to go purple. So here is atom 1. Actually, here, let me just draw a black line. Okay, on this, I'm going to go isotope 1 and isotope 2. Okay, so let's go ahead and take a look. Isotope number 1, let's say we are doing an isotope, and remember purple are protons, so this isotope is the element that has 2 protons. Can you guess which one that is? Time's up. It's helium. All right, so if these are the protons, and I think we did orange for neutrons, let's say this one has 1 neutron, and let's say this one has 2 neutrons. All right, now just for sake of fun, let's assume that these 2 atoms are neutral, like we said before, and that they have 2 electrons each that cancel out the charges of the 2 protons. So the only difference between these 2 isotopes, isotope 1 and isotope 2, is the number of neutrons. And if I write their elemental symbol, since remember your atomic number is your name tag, it doesn't matter how many electrons or how many neutrons you have, it only matters how many protons you have. So since both of these 2 elements have 2 protons, this one's helium, and this one is also helium. But they are just different isotopes of helium. All right, so now we know that different isotopes only differ in the number of neutrons, okay? And that's it. That's the last, you don't there are no more details than that really. And lots of elements, as a matter of fact, pretty much every element on the periodic table has isotopes. Sometimes there are only a couple, sometimes there can be several. All right, so the last thing I want to talk to you about is the mass number, okay? The mass is the average of the isotopes. So let me do a hypothetical. This is just a made-up example. Let's say, for example, and we're going to use carbon. Now, I want this to be clear. This is not exact. If you look up the mass of carbon, it's not going to be what I'm going to calculate, but I'm going to show you how they get to that particular mass. Remember, down here on the periodic table, you've got, for example, I'll just use hydrogen. It's got an atomic number of 1, meaning 1 proton, and then you think you have 1.0079 or 1.008. Why is it if the mass equals protons plus neutrons, and you don't have a half a proton or a third of a neutron, why is this a decimal? Okay, why in the world is this a decimal? How could that possibly be? Okay, well, remember, if you remember last time, I'll switch to blue now. If the example I gave when we talked about carbon dating was that there were 3 different kinds of carbon. And the way we write this is carbon, and I'm going to say carbon 12. Then there was carbon 13, and then there was carbon 14, the one they used for carbon dating. And if you remember, this is just the way we write these things. The top number, that is these numbers here, are the mass numbers, that is the protons plus the neutrons. And the numbers down here, I'm guessing you probably figured out, is the atomic number, which is just the number of protons. So since they're all carbon, they all have to have 6 protons because that's the number of protons carbon has. But up here on the top, carbon 12 has 6 neutrons, so 6 plus 6 is 12. Carbon 13 has 7 neutrons, 6 plus 7 is 13, and carbon 14 has 8 neutrons, 6 plus 8 is 14. Okay, so that's how we just write these things. Let's go to the next. So now, if let's say for example, 50% 50% of carbon were carbon-12. Let's say 25% of carbon were carbon-13, and 25% of carbon were, you guessed it, carbon-14. Okay, so let's assume that these are, in nature, the relative abundance of each one of these things. Okay, meaning that if I take a handful of carbon in nature, half of it's going to be carbon-12, a quarter of it will be carbon-13, and a quarter of it will be carbon-14. I can't pick out individual atoms, but let's say this is what it's like in nature. This is not what it's like in nature. It's much, much less for 13 and 14, but let's just assume this is what it is. Well, the way I get to that weirdo mass number is the following. Watch the math. Let's change to purple just for fun. If I go 12 times 0.5, that's 50%, that's going to give me 6. Okay, does everyone see that? I multiplied the mass of carbon-12 times its relative abundance, which is 50%. The next one I'm going to do is 13 times, and what's its relative abundance? 25%, 0.25. So if I multiply 13 by 0.25, I get 3.25. And the third calculation is 14, carbon-14, and again it's 0.25 according to my example. And if I go 14, that's 3.50. So if I add all of these up now, the mass times the relative abundance, I'm going to get 6, 7, 8, 9, 10, 11, 12.75. 12.75. Notice I get a decimal. And that's where it comes from. Now, if you look up on the periodic table, the actual mass is 12.011 or something like that, which means that most 99% of the carbon in the universe is carbon-12, with only a tiny little bit of carbon-13 and 14. But the math is the same. Whatever the mass is, you multiply it by its relative abundance, and that's how you get the average mass, taking into account all of the isotopes. Okay? So there you go.